Moving to the next question. A carbonyl compound. Here a halogen bromine. Here a halogen iodine. First step, reaction with the zinc. Second step, a diene under thermal condition. What will be the reaction? Okay, so alpha dihaloketone on reaction with the zinc metal and a dienophile under thermal condition. You know the function of metal. Metal will provide, zinc will provide 2 electron. Metal in most organic reaction, the primary function of the metal is to donate electron. So zinc will donate 2 electrons. So that in the first step, initially the first step, this compound undergo homolytic cleavage because the condition is thermal condition. So the bond will undergo homolytic cleavage. Br, here a radical, here a radical. Then in the next step, the 2 electrons from zinc, 1 electron to oxygen and 1 electron to this carbon. So in the next step, here not bromine, here iodine. Okay. The next step, bromine, here iodine. This is O radical, the 1 electron from zinc, then it becomes O minus. This is carbon radical, 1 electron from zinc, this become carbon minus. Then in the next step, elimination of a halogen. My question, here 2 halogens are there, iodine and bromine. Which halogen will be eliminated? You know about the leaving group tendency of halogen. Which halogen is the powerful or the better leaving group? Comparing the halide ion, leaving group tendency of I minus greater than, Br minus greater than, Cl minus greater than, F minus. This is the order of leaving group tendency of halide ion. So I minus is a better leaving group. So this negative charge will make a pi bond here. This I minus will be eliminated. So that in the next step here a double bond is there. Bromine and O minus. Bromine and O minus. One more, still the allylic cation is not generated. Still one more bromine is there. In the next step, neighboring group participation. We will discuss about a neighboring group participation in the general organic chemistry section. Here the second bromine is eliminated with the help of this pi bond. So this pi bond is shifted towards here. This Br group is eliminated. So that in the next step, double bond plus O minus. So an allyl cation is generated. So alpha dihaloketone on reaction with the zinc metal will provide 2 electron. After the elimination of the 2 second bromine is eliminated with the help of this pi bond. That is called as neighboring group participation. So that an allyl cation is generated. So in the second step, a dienophile is given. So allyl cation is generated. Then in the next step, a diene is given. Diene. So this allyl cation will react with the diene 1,3-butadiene in the thermal condition. Simply a 4+2 cycloaddition reaction. This pi bond will make a sigma bond with this carbon. This pi bond make a sigma bond with this carbon. This pi bond shifted towards these 2 carbon sides. So what will be the product? The cyclopropane ring as such. Here an O minus is there. Then here the 1,3-butadiene system. Here a new sigma bond is formed. Here a new sigma bond is formed. Here a pi bond is formed. Is it? That is O minus. Then in the next step, what will be the product? This O minus will make a pi bond here. So your product will be 1, 2, 1, 2, 3, 4, 5, 6, 7. Double bond O. A carbonyl compound will be your product. A carbonyl compound will be your product. Okay, clear? Clear? So, this allyl cation with an O minus will undergo 4 plus 2 cycloaddition reaction under thermal condition. So here a new sigma bond is formed, here a new sigma bond is formed, here a pi bond is there and an O minus. O minus will convert into double bond O, so that a carbonyl compound will be your product. Okay, then next question. A carbonyl compound, here a bromine is present, here also the same bromine is present, here a substituent, here a substituent. First condition, reaction with the zinc metal. Second condition, a diene is given. This is a diene, 1,3-butadiene under thermal condition. So what will be the reaction? Alpha-alpha dihaloketone on reaction with the zinc metal. First step, homolytic fission of the carbonyl bond. Homolytic fission of the carbonyl C double bond O bond. So C double bond O bond undergo homolytic fission to form 2 free radicals. Then in the next step, the two electrons from the zinc metal will donate 2 electrons. So that 2 electron will add to oxygen and carbon. So that bromine, here also a bromine. This O become O minus, carbon become C minus. Then in the next step, elimination. Since both are bromine, any bromine can be eliminated. So this minus will make a pi bond here. This bromine is eliminated. So your product will be O minus double bond. Here a substituent is there. Here Br. Okay. Then next step, the second bromine is eliminated with the help of the neighboring pi bond, neighboring group participation. So with the help of this neighboring pi bond, this pi bond will make this pi bond shift towards here. This bromine is eliminated. So your product, double bond minus so an allyl cation will be, stereochemistry is not at all important. So an allyl cation will be your product. An allyl cation with an O minus is also there. O minus. So this will be your product. So that undergo 4 plus 2 cycloaddition with the 1,3-butadiene. 4 plus 2 cycloaddition reaction. Four plus 2 cycloaddition reaction under thermal condition. So this pi bond will make a sigma bond here. This will make a sigma bond here. This move towards this side. So in the next step, O minus here a new sigma bond is formed, here also a new sigma bond, here a pi bond. Is it? In next step, this O minus converted to C double bond O. So a 7-membered ring. Here a pi bond, double bond O, 2 substituents. So that will be your final product. So first step, alpha-alpha dihaloketone react with the zinc metal followed by a 4 plus 2 cycloaddition reaction with the allyl cation. So in this question, the allyl cation is not directly given. Instead of the condition for the formation of allyl cation is given. Okay, the next question. So that will be your question. Okay, so a nice question. Here a pi bond is also there. 1 second. OH. Okay, so write the product. Write the product. Write the product. So 1, 2, 3. An allylic alcohol. Allylic alcohol on reaction with the triflic anhydride TF2O. What will be the reaction? Allylic alcohol on reaction with the acetic anhydride AC2O. OH is converted to OAC. Allylic alcohol on reaction with the TF2O, it will convert it into OTF. Actually, this acetic anhydride, triflic anhydride are alcohol protecting groups. Alcohol protecting group. OH is converted to OAC. In the presence of TF2O, OH is converted to OTF. So, allylic alcohol, OH is converted to OTF. OTF. SiMe3. This OH is converted to OTF, triflate, OTF, double bond, SPH. Then in the next step, OTF is a good leaving group. OTF is a good leaving group. OAC, OTF, then SiMe3, H2O, these are good leaving group. OAC is a good leaving group because that ion is resonance stabilized. OTF is also a good leaving group because that ion is resonance stabilized. H2O is a good leaving group because H2 is neutral. SiMe3 is a good leaving group because that positive charge is stabilized by that silicon. So since these are good leaving group, we will study about the leaving group in the general organic chemistry section. So OTF is a good leaving group. So in the next step, this pi bond will help in the elimination of this leaving group by neighboring group participation, NGP. So this intervening pi bond helps in the elimination of this OTF, so that in the next step, here a pi bond is formed. Here an SiMe3 is present. Here an SPH is present. And a positive charge is developed here because that pi bond is shifted. So a positive charge is developed. So this is an allyl cation. A diene is also present in the same molecule. So intramolecular 4+2 cycloaddition reaction. Intramolecular 4+2 cycloaddition reaction under thermal condition. Intramolecular 4+2 cycloaddition reaction under thermal condition. What will be the reaction? This pi bond will make a sigma bond here. This pi bond will make a sigma bond here. This shift towards this side. So you have to give a number. This is 1, 2, 3, 4, 5, 6, 7. A 7-membered ring is formed. A 7-membered ring. A 7-membered ring. 1, 2, 3, 4, 5, 6, 7. Again giving number. This is 1, 2, 3, 4, 5, 6, 7. Okay. At 1 an SPH is present. At 1 an SPH. And at 2 an SiMe3. Here pi bond is shifted, so at 2 a positive charge is developed. 3 and 4 make a new sigma bond. Between 5 and 6 a pi bond is there. 7 and 1 make a new sigma bond. So this will be the next step product. It's a carbocation, not stable. In the next step, elimination of H+. Next step, elimination of H plus will be eliminated. H plus will be eliminated. Alpha hydrogen. Alpha hydrogen. Here an alpha hydrogen is present. Here an alpha hydrogen is present. At carbon number 3 an alpha hydrogen is present. And then at this carbon also an alpha hydrogen is present. So elimination is the step. Elimination is the step. You know, compared to H plus, SiMe3 plus is a very good leaving group. SiMe3 plus is a very good leaving group that we studied in the previous lectures. Compared to H plus, here hydrogen can eliminated to form a double bond. This hydrogen eliminated, here a double bond. Here hydrogen and SiMe3, all these are in alpha position. Elimination is an alpha elimination. So my question, whether hydrogen or SiMe3, which will be eliminated? So compared to the H plus, SiMe3 is a very good leaving group. So definitely this SiMe3 is eliminated. SiMe3 is eliminated. So what will be your final product? A 7-membered ring. A 7-membered ring. 7-membered ring. Here a pi bond. Here an SPH group is present. SPH. Here a double bond is formed because SiMe3 is eliminated. So this will be your final product. If SiMe3 is not present here, most substituted alkene will be formed. But compared to the rate of elimination of H plus and SiMe3 is the good leaving group, which will be eliminated, and here a double bond is formed. So a nice question. Intramolecular 4+2 cycloaddition reaction. First step, allyl alcohol. In your exam, you have to identify that this is an allyl alcohol. Allyl alcohol on triflic anhydride, OH is converted to OTF. That is an alcohol protecting group, OTF. In the next step, this pi bond helps in the elimination of this OTF group by neighboring group participation. Then here a carbocation is formed, an allyl cation, intramolecular reaction with the diene. Then a 7-membered ring with a positive charge is formed. Next step is elimination. Whether hydrogen eliminated, whether SPH also can eliminate. So comparing hydrogen, SPH, SiMe3 is the SPH is also a good leaving group, but compared to SPH, SiMe3 is the very good leaving group. Okay, so here a new double bond is formed. So that is about that question. Okay, one thing I forgot. Here between 3 and 4 a new bond is formed. Here 2 carbons are still remaining. 2 carbons are still remaining between 3 and 4. So between 3 and 4, 2 carbon atoms is there. Okay, this is between 3 and 4, 2 carbon atoms, a 4-membered ring, 2 carbon, 2 carbons are there. So this will be your final product. So will be your final product. Okay. So that's all about the reactions of allyl cation and allyl anion 4+2 cycloaddition reaction. We discussed the generation of allyl cation. Generation of allyl anion is not at all important. The simple generation of allyl anion. Allyl anion can be simply generated. For example, consider this compound. This position is called the allylic position. This position containing 3 hydrogens. Okay. On reaction with a powerful base. On reaction with a powerful base. One of the allylic hydrogen is abstracted by the base, so that your product will be an allyl anion. Allyl anion. So the allylic hydrogen can abstracted by a base to form an allyl anion. So that is not at all important. So we can wind up that section. So our cycloaddition reaction is officially completed. The most important cycloaddition reaction is 4+2 cycloaddition reaction. One more cycloaddition reaction is there, that is 2+2 cycloaddition reaction. 2+2 cycloaddition reaction. This is also important. Consider these 2 molecules, a 2 pi electron system. This is also a 2 pi electron system. So how many electron pairs are there? 2 pi plus 2 pi, 4 pi electron. 4 pi electron means 4 by 2, 2 pair of electron. So two pair of electrons are involved in this cyclization process, so that cyclobutane is formed. Cyclobutane. Here a new sigma bond, here a new sigma bond. My question, how many electrons are involved in the cyclization process? 2 plus 2, 4 pi electron, that means 2 pair. 2 pair means an even number. Even number means the condition for the reaction is photochemical condition. So our 2 plus 2 cycloaddition reaction is a photochemical reaction. 2 plus 2 cycloaddition reaction is a photochemical reaction. So we will study about 2 plus 2 cycloaddition reaction in the photochemistry, not in pericyclic. Okay, so all the detailed aspects of 2 plus 2 cycloaddition we will discuss in the photochemistry section, because that is a photochemical reaction. 2 plus 2, total 4 pi electron, that means 4 by 2, 2 pair of electron. Definitely the condition will be photochemical condition. Photochemical condition. Okay, so we can study that in photochemistry section. Then other type of question that you can expect in the CSIR NET and GATE exam. For example, other type of question. How many pi electron? 4 pi electron. 4 pi electron. Plus, this is also a 4 pi electron system. So this is a 4 plus 4 cycloaddition. 4 plus 4 cycloaddition, because a 4 pi electron system and other 4 pi electron system. Here a new pi sigma bond is formed. This pi bond shifted towards here. Here a new sigma bond, this towards here. Okay. So 1, 2, 3, 4, 5, 6, 7, 8. An 8-membered ring will be your product. An 8-membered ring will be your product. Here a pi bond. Here also a pi bond. So that will be your product. This is a 4 plus 4 cycloaddition reaction. Our question, what is the condition? Thermal condition or photochemical condition? This type of question you can expect based on 4 plus 4, 6 plus 2 and other cycloaddition reaction. Okay, what will be the condition? What will be the condition? Here 4 pi electrons are there. Here also 4 pi electrons. So 8 pi electron. 8 pi electron means 8 by 2. 4 pair of electron. 4 is an even number. Even number, therefore the condition will be photochemical condition. Condition will be photochemical condition. So 4 plus 4 cycloaddition reaction takes place under photochemical condition. Okay. Then next, one more question. One more question. How many pi electron? 2, 4, 6. 6 pi electron plus 2 pi electron. So what is the type of cycloaddition? 6 plus 2 cycloaddition reaction. 6 plus 2. Okay, what will be the product? Here a new sigma bond. This pi bond towards here. This towards here. Here a new sigma bond is formed. So your product will be 1, 2, 3, 4, 5, 6, 7. An 8-membered ring will be your product. 1, 2, 3, 4, 5, 6, 7, 8. An 8-membered ring will be your product. What is the position of the pi bond? Position of pi bond. Give a number. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Between 2 and 3, a pi bond is formed. Between 4 and 5, a pi bond is formed. So this will be your final product. Okay. What is the condition? That's our question. Whether this reaction takes place under thermal or photochemical condition. What is the condition? How many electron pair? 6 plus 2, 8 pi electron. 8 by 2, 4 pair. 4 pair is an even number. So definitely condition is photochemical condition. Okay, so our detailed aspects is only 4 plus 2. 2 plus 2 will discuss in photochemistry. Then this type of questions you can expect based on 4 plus 4, 6 plus 2 condition, whether 2 plus 2 or, so whether thermal or photochemical. So that's all about cycloaddition reaction. So first we discussed about electrocyclic reaction, then cycloaddition reaction. So both the topics are completed. Our next type of pericyclic reaction, third one, sigmatropic rearrangement. Okay, sigmatropic rearrangement. First pericyclic reaction is electrocyclic reaction. Electrocyclic reaction is shown by a conjugated system, a conjugated polyene, like that a strained ring system undergo electrocyclic ring opening. So such systems is shown electrocyclic reaction. Second one is cycloaddition reaction, which is shown by two components are there. In cycloaddition reaction, two components are there, a diene or a dienophile, diene plus dienophile. Okay. In sigmatropic rearrangement, one of the important reaction in organic chemistry, sigmatropic. Sigma bond means single bond is called sigma bond. Carbon-carbon single bond is called sigma bond. Sigmatropic rearrangement is shown by allylic system. Sigmatropic rearrangement is shown by an allylic system. So that's the most important point. In your exam, you have to identify whether it is a sigmatropic or not. Allylic systems are typically shown which type of reaction? Sigmatropic rearrangement. So the first one, type of systems that shows sigmatropic rearrangement. Type of systems that shows sigmatropic rearrangement. The typical systems that show sigmatropic rearrangement is allylic system. For example 1, please listen. Okay, so this is an sp2 hybridized carbon. The carbon connected to an sp2 hybridized carbon is an allylic carbon. A carbon connected to double bonded carbon, that is an allylic carbon. So this is an allylic carbon. This carbon is also allylic because it is also connected to a double bond. So here two allylic carbons are there. So definitely this will shows sigmatropic rearrangement. So sigmatropic rearrangement is shown by those systems which having an allylic carbon. Here two allylic carbons are present. Then second example. This is this type of system. Whether allylic carbon is present, this carbon is connected to a carbon-carbon double bond. So this is an allylic carbon. This is also an allylic carbon because it is also connected to a carbon-carbon double bond. So this system also shows sigmatropic rearrangement. Wherever allylic carbon is present, definitely sigmatropic rearrangement is shown by that system. Then third example. S double bond OPH, a sulfur oxide. S double bond OPH. Please listen. This is a carbon which is connected to a double bonded carbon. So this is also an allylic carbon. So definitely that sulfur oxide. This is an sp2 hybridized carbon. This is also sp2. This is sp3. That sp3 hybridized carbon connected to an sp2 hybridized carbon is called as allylic carbon. So that sulfur oxide will also show sigmatropic rearrangement. Then selenium oxide, fourth example, selenium oxide, Sc double bond OPH. Here also this carbon is a allylic carbon, so definitely this system will also show allylic system. In CSIR exam point of view, first thing is you have to familiarize the systems that shows the particular reaction. Then only you can identify that particular compound in the exam. Okay, so these all systems shows sigmatropic rearrangement because here allylic carbon is present. Allylic carbon is present. Then another nitrogen oxide, nitrogen N O minus CH3 nitrogen oxide. Here also an allylic carbon is present. So that compound, that system will also show what type of reaction? Sigmatropic rearrangement. Then another one. Another system. Please listen. This system also show sigmatropic rearrangement because this carbon is connected to a double bonded carbon. So this is an allylic carbon. This is also an example of an allylic carbon. Okay. Then another example. This is also, here also allylic carbon is present. This carbon is allylic carbon that is connected to a carbon-carbon double bond. So this will also show sigmatropic rearrangement. Then another one. This carbon is allylic carbon. So this system also shows sigmatropic rearrangement. Here also allylic carbon is, wherever allylic carbon is there, definitely sigmatropic rearrangement is shown by that system. Then another one. Instead of sulfur oxide, sulfur ylide is given. Instead of sulfur oxide, sulfur ylide is given. S plus CH2 minus, two charges on neighboring. This is a sulfur ylide and this carbon is an allylic carbon. So definitely that sulfur ylide also shows sigmatropic rearrangement. Another example. An oxygen ylide, ORCH2 minus, oxygen with 3 valency plus. This is here also an allylic carbon is present that will also show sigmatropic rearrangement. So these are some popular systems that show sigmatropic rearrangement. So the first condition or the first thing that you have to study in sigmatropic rearrangement, a system having allylic carbon definitely shows what type of reaction? Sigmatropic rearrangement reaction. Okay, then numbering or nomenclature. In sigmatropic rearrangement. Numbering or nomenclature in sigmatropic rearrangement. So please listen. Numbering or nomenclature. First point that you have to memorize, numbering always from allylic carbon. Numbering always from what? Which carbon? Allylic carbon. Numbering always from allylic carbon. So that is an important point. For example, this is a typical system that shows sigmatropic rearrangement due to the presence of two allylic carbon. Here, two allylic carbons are there. Numbering always from allylic carbon. So this is an allylic carbon. So that allylic carbon is given the number 1. Always the allylic carbon, you have to give the first number to the allylic carbon. So this is carbon number 1, carbon number 2, carbon number 3. Then in the opposite side also 1, 2, 3, and this bond is called as a 1-1 bond. So wherever the allylic carbon is present, that carbon is 1, then 2, then 3. Then the opposite side again 1, 2, 3. 1, 2, 3. Clear? Clear? Then in the next example, next system that shows sigmatropic rearrangement. Pi bond, pi bond, pi bond, pi bond. Which is the allylic carbon here? This carbon is an allylic carbon. Allylic carbon. So give the first number to the allylic carbon. Allylic carbon is 1, 2, 3, 4, 5. Then in the opposite side also again give 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this is the 1, 1 bond. 1, 1 bond. Clear? So this is the 1, 1 bond. Then another system. Another system. Yes. Sorry. Yes. Double bond O pH. S double bond O pH. Which is the allylic carbon? Here this is the allylic carbon. A sulfur oxide. An allylic carbon is present. Allylic carbon is present. So allylic carbon is given the number 1. 1, 2, 3. 1, 2, 3. In the opposite side also give 1, 2. 1, 2. Here sulfur and oxygen is the reacting system. So 1, 2. So this is the 1, 1 bond. 1, 1 bond. Then a selenium oxide. Selenium oxide. Double bond allylic carbon Sg double bond O pH. This is a typical system which shows sigmatropic rearrangement due to the presence of an allylic carbon. So that allylic carbon is given the number 1, then 2, then 3. Then in the opposite side also again 1, 2. So this is called as the 1, 1 bond. This 1, 1 bond is very, very important. 1, 1 bond is very, very important. Then a nitrogen oxide. Nitrogen oxide. Nitrogen oxide. NO minus CH3. O minus CH3. This is an allylic carbon. Definitely sigmatropic rearrangement is shown by that system. So the allylic carbon is given the number 1, then 2, then 3. Then in the opposite side also 1, 2. So this is called as the 1, 1 bond. 1, 1 bond. Then an ylide. For example, sulfur ylide. Yes. pH. Instead of oxide, CH2 minus and sulfur plus. Sulfur plus. This is the allylic carbon. Give allylic carbon 1, then 2, then 3. Then in the opposite side also 1, 2. CH2 minus 1, 2. So this is called as the 1, 1 bond. So always numbering is from the allylic carbon. Another example. Another example. Whether this system shows sigmatropic rearrangement? Yes, because an allylic carbon is present in the system. So give 1, 2, 3. 1, 2, 3. Then in the opposite side also you have to give a number. In the opposite side here only a hydrogen is present. So that hydrogen is 1. So this is called as the 1, 1 bond. Then another system. Okay, which is allylic carbon. This is the allylic carbon. Give that carbon 1, 2, 3, 4, 5. Then in the opposite side also you have to give a number, but here only a hydrogen is present. So that hydrogen 1, so this is the 1, 1 bond. 1, 1 bond. Then another system. Okay, this is an allylic carbon, that is 1, 2, 3, 4, 5, 6, 7. Then in the opposite side here only a hydrogen is present. So that is also 1. So this is called as a 1, 1 bond. That 1, 1 bond is very, very important in sigmatropic rearrangement. So that is about the type of systems and the nomenclature or numbering of the system. Numbering always start from allylic carbon. You have to give the allylic carbon as number 1. Okay, then reactions. Directly moving to reactions. Throughout the lecture, one thing that you have to remember is, in the reaction, breaking of one sigma bond. That is the important thing. Okay, breaking of one sigma bond. That is simply sigmatropic reaction. The breaking of one sigma bond. For example, consider the system, a typical system that shows sigmatropic reaction, because here an allylic carbon is present. Then what is the nomenclature? Carbon allylic carbon is 1, this is 2, this is 3. Then in the opposite side also 1, 2, 3. So reaction is breaking of one sigma bond. So this is the one sigma bond. That bond undergo cleavage. One bond undergo breaking. So here a new sigma bond is formed. This shifted towards this side. Okay. So one bond is break. 2, 3. Here between 3 and 3 a new sigma bond is formed. So the product will be again giving number. This is 1. This is 2. 3. Here also 1, 2, 3. 1, 2, 3. So one bond is undergo breaking, and between 3 and 3 a new bond is formed. So the name of the sigmatropic rearrangement is, wherever the new bond is formed, new sigma bond is formed between 3 and 3. One bond undergo breaking, and a new sigma bond is formed between 3 and 3. So that is the name of the reaction. This is the newly formed sigma bond. So new sigma bond is formed between 3 and 3. So this is a 3-3 sigmatropic rearrangement. Okay, wherever the new sigma bond is formed, that is the name of the reaction. Wherever the new sigma bond is formed, that's the name of the reaction. So new sigma bond is formed between 3 and 3. So that is a 3-3 sigmatropic rearrangement. So what is the reaction? Breaking of one bond. So one bond undergo breaking, and 3-3 a new sigma bond is formed. So the new sigma bond is formed between 3 and 3. So this is an example for a 3-3 sigmatropic rearrangement. Here a pi bond is present. Between this a pi bond is present. So that is the first example. Then second example. So name of the sigmatropic reaction is wherever the new sigma bond is formed. Example 2. Example, typical system which shows sigmatropic rearrangement, because 2 allylic carbons are there. This is 1, 2, 3, 4, 5. Then in the opposite direction also the same number, 1, 2, 3, 4, 5. So this is the 1 bond. So reaction, sigmatropic reaction is the breaking of 1 sigma bond. So 1 sigma bond undergo breaking. This pi bond towards here. Here a new sigma bond is formed. This pi bond towards here. This towards here. So what will be the product? Again giving number 1, 2, 3, 4, 5. Here also 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So 1 bond undergo breaking. Between 5 and 5 a new sigma bond is formed. So this is a newly formed sigma bond at 5 and 5. So this is an example of a 5-5 sigmatropic rearrangement. 5-5 sigmatropic rearrangement. Then between 1 and 2 a pi bond is formed. Between 3 and 4 a pi bond is formed. Between 1 and 2, here also a pi bond. Between 3 and 4, a pi bond. So that will be your new product. So that is an example for a 5-5 sigmatropic rearrangement. 5-5 sigmatropic rearrangement. Okay. Then next example. 3. Example 3. Okay, whether this system shows sigmatropic rearrangement? Definitely, because an allylic carbon is there. So giving number allylic carbon 1, 2, 3. Then in the opposite direction also, here only a hydrogen is present. So that is also 1. That is also 1. So what will be the reaction? What will be the reaction? Breaking of 1-1 sigma bond. So 1-1 bond undergo breaking. So here a new sigma bond is formed between 3 and 1. So what will be the product? Here a pi bond. Then that hydrogen here. Is it? No. Hydrogen. Please give a number. This is 1, 2, 3. New sigma bond is formed between 3 and 1. This is 1. Okay. So 1-1 bond undergo breaking and 1-3 bond is formed. So new bond is formed between 1 and 3. So this is a 1-3 sigmatropic rearrangement. This is an example for a 1-3 sigmatropic rearrangement. Okay, 1-3. Then next example. Example 4. Example 4. Whether this system shows sigmatropic rearrangement? Definitely, because an allylic carbon is present. So give 1, 2, 3, 4, 5. Then in the opposite direction also you have to give a number, but here a hydrogen is present. So hydrogen is also 1. What's the reaction? Breaking of 1-1 sigma bond. So this 1-1 sigma bond undergo cleavage. Here a new pi bond. New sigma bond between 5 and 1. New sigma bond between 5 and 1. So here a pi bond is formed. This pi bond shifted towards this side. Here a new sigma bond formed between the hydrogen. Give a number. This is 1, 2, 3, 4, 5. New sigma bond between 5 and 1. So 1-1 bond break, 1-5 bond is formed. So what is the type of sigmatropic rearrangement? 1-5 sigmatropic rearrangement, because new sigma bond is formed between 5 and 1. Then another example. Fifth example. A typical system that shows sulfur oxide. Sulfur oxide is S plus O minus. S double bond O can be represented as S plus O minus. Whether this system shows sigmatropic rearrangement? Definitely, because an allylic carbon is present. So 1, 2, 3. Opposite direction 1, 2. So what is the 1-1 bond? 1-1 bond. This is the 1-1 bond. So 1-1 bond undergo cleavage. O minus will make a new sigma bond here, this towards here. Okay, so 1-1 bond undergo cleavage, this minus make a new sigma bond here, this pi bond towards here. So your product, this is towards the sulfur. Here a new between 1 and, please give a number. This is 1, 2, 3. Between 1 and 2 a new pi bond. 3 is connected to the oxygen, and this oxygen containing the sulfur and pH. Oxygen containing the sulfur and pH. So 1, this is also 1, 2. So new bond is formed between 2 and 3. New bond is formed between 2 and 3. This bond back to the sulfur. So the positive charge on sulfur become neutral. So new bond is formed between 3 and 2. So this is an example for a 2,3 sigma tropic rearrangement. An example for a 2,3 sigma tropic rearrangement. Another example. Another example. Question number 6. Selenium oxide. SeO minus plus pH. SeO minus plus pH. So this minus, give a number. This is the allylic carbon. 1, 2, 3, 1, 2. So this minus make a new sigma bond here. This pi bond shifted towards between 1 and 2. This bond back to the selenium. Back to the selenium. Because selenium is positive. So what will be the product? Between 1 and 2, a new pi bond. 1, 2, this is 3. 3 is connected to the oxygen. 3 is connected to the oxygen. Oxygen is connected to selenium pH. So 2, 1. So new bond is formed between 3 and 2. So this is an example for a 2,3 sigma tropic rearrangement. So reaction is always the breaking of 1,1 bond and the forming of a new bond. Wherever the new bond is formed, that is the name of the sigma tropic rearrangement. Then condition. That means whether the sigma tropic reaction takes place under thermal condition or photochemical condition. If electron pair count is odd, like the 4+2 cycloaddition reaction or the photochemical cycloaddition reaction, similar to the cycloaddition reaction, if electron pair count is odd, reaction takes place under thermal condition. If electron pair count is even, reaction takes place under photochemical condition. So that is the key point. Okay. If your electron pair count is an odd number, reaction will be under thermal condition. If electron pair count is an even number, reaction will be feasible under photochemical condition. For example, a sigma tropic rearrangement. An allylic carbon is present. This is the allylic carbon. So that is 1, 2, 3. In opposite side here a hydrogen is present. So hydrogen is 1. So what's the reaction? Breaking of 1,1 bond. Breaking of 1,1 bond, here a new sigma bond is formed. So your product will be here a new hydrogen. So 1, 2, 3. This is also 1. So new bond is formed between 3 and 1. So this is a typical example for 1,3 sigma tropic rearrangement. Okay. How many electrons are involved in the whole process? 2 pi electron and 2 sigma electron. 2 pi electron and 2 sigma electron. So how many electron? 2 plus 2, 4 electron. 4 electron means 2 electron pair. 4 electron means 2 electron pair. So that 2 is an even number. Then this reaction takes place under photochemical condition. If electron pair is even number, then that reaction will take place under photochemical condition. Another example. Okay. What will be the reaction? Allylic carbon. 2 allylic carbons are present. 1, 2, 3. 1, 2, 3. Okay, 2 allylic carbons are present. What will be the reaction? Breaking of 1,1 bond. So 1,1 bond undergo breaking. Here a new sigma bond is formed. So your product will be, okay, again giving number 1, 2, 3, 1, 2, 3. 1,1 bond undergo breaking. 3,3 bond is formed. Okay, between 1 and 2 a pi bond. Here also a pi bond. Okay, so what is the name of the reaction? 3 plus 3, because new bond is formed at 3 and 3. So 3 sigma-tropic rearrangement. My question, whether thermal condition or photochemical condition. How many electrons are involved in the process? 2 plus 2, 4 pi electron and 2 sigma electron. Okay, 2 plus 2, 4 pi electron and 2 sigma electrons are involved. So total 6 electron. 6 electron means 3 pair of electron. 3 pair of electron. 3 pair of electron is an odd number, so definitely this reaction will be feasible under thermal condition. So that is a condition for the reaction. If electron pair count is odd, reaction is thermal. If electron pair count is even, that is photochemical. Okay, so that is a basic introduction to sigma-tropic rearrangement. An introduction to sigma-tropic rearrangement. So many sigma-tropic rearrangements are there. 3 sigma-tropic, 2 3, then 3 5. Many sigma-tropic rearrangements are there. Among these, the most important for your CSIR NET and GATE exam is the 3 sigma-tropic rearrangement. 3 sigma-tropic rearrangement is the most important sigma-tropic rearrangement. Okay, 3 sigma-tropic rearrangement is the most important sigma-tropic rearrangement. Please listen. This 3 sigma-tropic rearrangement, 3 sigma-tropic rearrangement, most important for any higher chemistry related competitive exam. Two typical examples for 3 sigma-tropic rearrangement. First one, Cope rearrangement. A typical example for a 3 sigma-tropic rearrangement is Cope rearrangement. Another typical example is Claisen rearrangement. So Cope rearrangement and Claisen rearrangement. Okay, this Cope rearrangement is again classified into four types. All these are important. Cope rearrangement are of 4 types. First one, simple Cope. Second one, oxy-Cope. Third one, azacope, and fourth one, oxy-azacope. So 4 types of Cope rearrangement. All these are 3 sigma-tropic rearrangement. That is the importance of 3 sigma-tropic rearrangement in pericyclic, and that's for the important for your exam. Okay, so 3 sigma-tropic rearrangement, 2 typical example, Cope rearrangement and Claisen rearrangement. This Cope rearrangement again, simple Cope, oxy-Cope, azacope and oxy-azacope. This Claisen rearrangement is again 3 types. First one, simple Claisen rearrangement. Then next one, Ireland-Claisen rearrangement. One second. Ireland-Claisen rearrangement. Third one, ortho-ester-Claisen rearrangement. So 4 plus 3, 7 reaction that we have to discuss. After that, a major portion of sigma-tropic rearrangement that we can complete. Okay, so 3 sigma-tropic rearrangement, Cope rearrangement and Claisen rearrangement. Cope rearrangement again 4 types: simple Cope, oxy-Cope, azacope, oxy-azacope. Then Claisen rearrangement again 3 types: simple Claisen, Ireland-Claisen, very important, and ortho-ester-Claisen. And the stereochemistry of all these reactions. Stereochemistry is the major core part in this Cope rearrangement. Stereochemistry of all these reactions that we have to discuss in the next lecture.